Welcome back, Precalcsters. In this video, if you're watching it, you are here hopefully for a couple extra examples. And I have chosen just two arbitrary examples, ones that look like they might be kind of challenging. And I'm just going to talk through it. So no pausing. If you want to pause it, I would encourage keep like your finger on the cursor, be ready to pause it because I'm just going to blast through. So these are additional verifications from 5.2. And let's go ahead and jump right in. So this is number 14 from the assignment, which you didn't have to do. It's an even, but the odds, you can't really check your answers either, so really it doesn't matter. But I'm looking at this one, and I'm trying to verify that this is indeed true. Now, right off the top of my head, I haven't done this problem, don't have anything in front of me, so what you see and what you hear is me thinking through this in live time. So right off the bat, I believe that this side looks a little bit more complicated. Now, if I wind up being wrong, that's okay, but I'm going to start with this side. So here we go. As I examine this couple different things, I realize that I need to wind up with only cosine squareds. So my first initial thought is if I have a sine squared here, maybe there's a way that I can change it. So I'm going to use a Pythagorean identity and just see where it takes me. Cos squared beta, nothing changes, minus, and I'm going to go ahead and replace a sine squared with a cosine squared minus 1. So again, I'm just rearranging this up here. I could solve this for negative sine squared, or sine squared if you will, and if I solve it for sine squared, I'm going to get 1 minus cosine squared. And just to comment on the previous little thing that I said, as I looked at this, I saw negative sine squared, so I thought about solving this for negative sine, but I will just solve it for positive sine and keep the negative outside. So this is what the left side of this becomes. So I'll just go ahead and annotate that's Pythagorean theorem, or as I shorthand, Pytherem. Cool. So next line here then, and I'm going to go with a darker red, I don't like that one. I'm just going to rearrange and clean stuff up a little bit. So we get a cos squared beta, and I'll distribute, so minus 1, and then plus cos squared beta. And look at that. On our very next line, I'm going to combine any like terms, and I see that there is a cos squared plus a cos squared. Gets me 2 cos squared beta minus 1, which is exactly what I was asked to wind up with. And we have it. Now, I didn't specify this in class, but I want you to notice something. We've elected to start with the left side, and I did. However, if instead of working down like this, I started here and started working up, we get the opposite direction of the proof. Now, it's hard to start from something simpler or less expressed anyway and work backward, but it is possible. So, cool. Number 14, knocked out. Awesome. So looking at number 22, it is a very different feel. And what I recognize is this problem looks like it might be from calculus. And there's some motivation here that's going to make stuff easier, because when you get to calculus, there's things called derivatives and integrals. And this is awful to do either of those things with. This one, nowhere near as bad. So as I look at this problem, my gut is saying that, man, this side is rough. Now, again, I haven't worked through this, didn't look at it beforehand, so we're just going to kick right in. Immediately, what I notice is both of these things have a secant x, tangent x. Now, I need a secant tangent left over, so I'm going to go ahead and factor that out from each of these terms. Secant x, tangent x factors out, and then I'm going to use brackets just so it's a little bit more clear. And I remain, and there's going to be another piece that I didn't see at first, but that's okay. I have a secant to the 6th x minus a secant to the 4th power x left over. So here we are. All I have done in this situation is factor. Cool. Now, more so, I didn't see it at first glance, but I see it now. There's a larger greatest common factor. So I used the language the other day in class, least powers. where I have essentially the same variable. It's a secant x is what I'm assuming or acting as though my variable is. And I see a secant or a variable to the 4th power and a variable to the 6th. So I'm going to go ahead and factor out the least power that I can, and that's the smallest power, and I'm going to pull a secant to the 4th out. Now, I'm combining secant to the 4th x that would move out front, and I'll show this step. Secant to the 4th x, that's the additional piece I factored out there, but I still had secant x right here, and tangent x. And if I factored out a secant to the 4th, it looks like I get a secant squared x minus 1 left inside. Now, what I wanted to do, but I want to be really clear with my work, is I wanted to just skip this middle line and do it all after I'd made the comment. So more factor is what happened on that previous line, and I'm just going to say least powers because that's what I factored out, the smallest power of the variable that I had in the list or in my expression. Cool. So here we go. I'm going to recombine these, and I get a secant to the 5th power of x times a tangent x. That is just me simplifying. And then inside this bracket, I see secant squared minus 1. And my brain is just screaming Pythagorean theorem. So I'm looking, I see, well, this third one right here, if I subtracted 1, it's secant squared minus 1 can be replaced by tan squared. So I'm going to go ahead and do that. Tan squared x. And once again, step 3 here, this is just another Pythagorean theorem. And all of a sudden, I have no more factoring to do. These brackets are there to help me keep stuff straight, but they really just indicate that I should multiply stuff. So here we go. I wind up with a secant to the 5th x times tan x times tan squared, which is going to give me a tangent cubed x. And look at that, secant to the 5th tangent cubed, and I forgot an x when I wrote that, my bad. And here it is. We're done. Now, these black boxes, I want you to make a habit of it. That, or if you would rather, we can use fancy math language, quadrat demonstrandum, QED. Either one of these is indicative that we have completely finished a proof. Cool. Now, these problems, I hope, are starting to feel easier as you get more and more comfortable with them, but there's one remaining technique that we just have not looked at yet. So this one, if you want to add it to your notes, cool. If you don't, also cool. But I'm going to sneak in one more additional example where maybe sometimes I start with a side and I decide throughout the process that it just gets too gross, too ugly, I can't deal with it. Instead of completely crossing stuff out and trying something else, from time to time, it may be worth it to pause and switch to the other side. So this example, I'm going to say sides separately. And I wish I could tell you that there's a standard way to recognize that you can do this or that you should do this. In reality, you could do this with any problem, but let's take a look at it. So let's say I want to verify the following. And it's a terrible looking fraction, but we have sine theta times tangent squared theta in this numerator. And we're going to divide this bad boy by secant theta minus 1. Okay, and I am told that this is exactly equal to cos theta plus 1 divided by the cotangent of theta. Now, right off the bat, one of the things that I recognize as I look at this is I don't know that I really say either side is uglier. So looking and just getting started, I'm going to do this side in red and just see if I can get to a point where it starts to look awful. So here we go. As I'm looking at this, I recognize that there's a secant theta minus 1 down here. And even a little step further, I see a tangent squared in the numerator. So here are these guys from earlier. There's a connection between tangent squared and secant squared. And I don't know if it's going to pan out or not, but I'm going to try it. and let's just see what happens. So here is me applying my Pythagorean identity to this tangent. So here we go. I would be on the left side. I would have sine theta, and I'm going to replace this with secant squared theta minus 1. And this is just, again, I want to stress this Pythagorean identity, secant squared minus 1. Okay, all of that still gets divided by secant theta minus 1. And at first glance, it might seem like we haven't really done anything. I've used an identity, and that's all fine and dandy, and I notice things kind of match, but remember, we have to have a single factor in the numerator divide out with a single factor of the denominator. So I can't just cross these out. That is not allowed, which means I need to do a little bit more thinking. But this secant squared theta minus 1, as triggy as it looks, it's just a difference of squares. So I have secant squared, whose square root is secant, and 1, whose square root is 1, and it's a difference. So I'm going to go ahead and factor this using the difference of squares. Secant theta plus 1 and secant theta minus 1. And in recognizing this, we hopefully can see that, man, if I can get one of these Pythagorean identities, it's going to be a difference of squares, which means when I have this down here, secant theta minus 1, what I recognize is I do have a factor of the denominator. Secant theta minus 1 is the factor that is exactly equal to a factor of the numerator. Now, it may feel like we're cheating from time to time, but if I add these parentheses around the denominator, I think it becomes a little bit more clear that those divide out. So let's just see where we wind up. Remaining, I have sine theta times secant theta plus 1. And maybe there's a little bit more that I can look at doing, and I don't know, it's kind of hard to think about. I don't have a cosine in here or a cotangent or anything like that. So it might be worth the time. I don't know, I might stop here, but looking at it, I see one more obvious thing just to get it easier to think about. I have sine theta times, and I'm going to clean this up just a little bit, secant by the reciprocal identities is 1 over cosine theta. And then instead of writing plus 1, I'm going to go ahead and just write, you know, I lied. I'll do plus 1. I was tempted to write it as a single fraction, but let's see. I'm just stepping until I reach a point where I don't see anything else super obvious. Now there's distribution, and let's see. I get sine over cosine, which winds up being tangent theta, plus a sine theta. All right, so this is significantly simpler, and I didn't annotate as I was going, but I don't know, maybe I could switch to sines and cosines, and there's probably a way to make this shake out nicely if we just keep stepping and trying stuff. But at this point, we've done 1, 2, 3, 4, 5 lines of work. Maybe, just maybe, it's not worth the additional effort. Now, I'm going to switch my focus. I reached a point where maybe there was no obvious choice. So notice the color difference. I'm not going to cross anything out. I haven't done anything wrong. I just want to see what happens, just maybe, if I try this right side. So as I look at this right side, I have cos theta plus 1. That's all fine and dandy, sorry. And I'm dividing this thing by cotangent theta. Now, rather than dividing, what I'm going to do is I'm actually going to think about this as multiplying by 1 over cotangent, which is the same thing, or the reciprocal of tangent. So I'm going to write that out in 2 steps. Instead of dividing by cotangent, that's the same as doing this. And on my next line then, I would get cos theta plus 1 times the tangent of theta. Cool. Now, if I want to distribute, I can, but maybe, just maybe, it would be a little bit nicer to distribute here first, or to change, because it's hard to think about tangents. So just to get a little bit of clarity, I'm going to take cos theta plus 1, And I recognize that this is going to multiply by sine theta over cosine theta. And that parentheses is ugly, but it exists. So I know it looks a little bit uglier, but sines and cosines are so much easier to think about. And let's just see where this takes me. So if I distribute here, I see my cos thetas would divide out, and I would simply be left with a sine of theta. And then plus, when I distribute here, because I'm looking back at this left side as I'm working, well, I could write sine theta over cos theta, but we know that that is just tan theta. Now, here is the super cool part of this problem. Once I get to this point, notice, without manipulating anything outside of the regular rules of multiplying by 1 or rewriting, I see that the left side can be transformed into an expression that is exactly the same as the right side. Now, in this situation, we didn't have to go all the way from the left to the right, but instead we took the left side, changed it, took the right side and changed it, and we got to a point where we recognized that these things were in fact equal. So as soon as this happens, we're going to go ahead and say, therefore, the identity holds. And we don't normally do this formal language. The identity is true. We have transformed it. We're done. Which means we now have a new trick up our sleeve. If we can make the left side and the right side be identical without using any properties of equality, then we have a new technique to prove this. All right. So I'm just kind of going through looking at any of your last examples that we might have. And I'm looking specifically, I see number 29 and 30. And I know you didn't do 30, but it looks like it might be interesting enough. So we've done 3 examples thus far. And I want to do one more just to make sure that we've hit all the bases. And I'm picking these based on what I think look like challenging problems, or what I'm assuming might be challenging for you. So last example, and this is number 30 in the textbook. We get cos theta cotangent theta, and this is a fraction. Cos theta cotangent theta. And we're going to divide this by 1 minus sine theta. And maybe we'll just sneak a new technique in here as well. And allegedly, if I take this whole expression, cos theta cotangent theta, over, and I'm just rereading it to make sure I don't have a typo, 1 minus sine theta, and I subtract 1 from it, allegedly, for any theta, this is exactly equal to cosecant. Cool. So, as we look at this expression, there's several different options that come to my mind, and let's just jump right in. I'm just going to try stuff. Again, haven't worked this problem, just thinking it out as I go, which is exactly what you should do. Don't be afraid to just be wrong. If I'm wrong, cool, I learned something that doesn't work. But if I'm right, cool, I learned that I'm getting better, and it did work. So either way, we win. So let's check it out. Looking at this expression, the first thing that I do not like about it is the fact that these do not match. So I'm going to make a common denominator. So cos theta cotangent theta over 1 minus sine theta minus, and I'm going to write this as 1 minus sine theta. I'm just rewriting my 1 here, over 1 minus sine theta. Cool. So that's my first gut instinct. We'll see if it shakes out. In the numerator then, I wind up with cos theta cotangent theta minus, and here's where it gets weird because there's really parentheses here. So it's minus 1 plus sine theta. Cool. And this is all divided by common denominator now, 1 minus sine theta. Now, I don't know that I really think it's gotten a whole lot nicer. I don't see any clear cosecants except there's a sine in the denominator here. And I just want to see what shakes out. So only thing that I don't like about this right now is this pesky cotangent. So I'm going to replace this cotangent right here using the quotient identity, and let's just see what happens. Cos theta times, and cotangent is cos theta over sine theta, minus 1 plus sine theta, still remaining in the numerator. And this all gets divided by that 1 minus sine theta. All right. So here we go. I see that when I do this multiplication, I wind up with a cos squared theta over sine theta. Then I still have a minus 1 plus sine theta. And this is all still divided by that 1 minus sine theta. All right. So as we continue to look at stuff, I realize that I have walked myself right into a complex fraction with fraction over fraction, or fraction within a fraction, sorry. And here we go. Let's just keep rolling. I am not giving up yet. So I recognize that if I made every denominator here sine theta, I would have a common denominator in the numerator, which I know that language is ugly, but I'm going to multiply this 1 by sine over sine and this by sine over sine. And instead of dividing by 1 minus sine theta, I'm going to think about it as multiplying by 1 over this. So here we go. We get cos squared theta. And then again, this guy multiplies by, this 1 rather, multiplies by sine over sine. So it would be minus sine theta. And then plus, this one also needs a sign in the denominator to match up with this. It would wind up being a sine squared theta. And all of that is now just the numerator, so just this piece. All of that is now over sine theta. Cool. This is going to work. I can see it's going to work. Now, I also need to multiply by 1 over 1 minus sine theta. And you can keep this as a fraction if you'd like. I would much rather multiply by the reciprocal than think of it as a single fraction. So here's this lovely expression, and I'm going to work up this way as we continue. And I'm nearing the end. Okay, in this numerator, there's a lot of different stuff that I could do. And looking at it, my first thought is I'm going to rearrange just a little bit. So what I mean by that is instead of writing cos squared minus sine plus sine squared, and I wouldn't normally show this step, but trying to be really, really transparent with it, I can rearrange this to be cos squared plus sine squared minus sine. And I'm going to have to move all of this over just a little bit. So we'll get rid of that. We'll select this guy here. Don't like that. Really don't like that. We're going to undo it. And I'm going to select something else. Maybe, if it'll let me. Here we go. So I'm just going to move this whole thing this way. And I'll try to make it so it's varied so it doesn't look like it's just stepping into the next one. So really, really clear here. I think I'm going to have a different color purple, which is my bad. But here we go. This, really bold to distinguish, works from here. All this line right here now works up to here. All right. So we are rolling through this. Sorry about that. This is just the numerator, this piece that we've just cleaned up. So this is still over sine theta. And we're going to still multiply by 1 over 1 minus sine theta. And the light at the end of the tunnel now exists. Because check it out. This expression, cos squared plus sine squared, that piece right here, it's 1. That's a Pythagorean identity. This is exactly equal to 1, which means up in the numerator, I now have a 1. I'll make that a little bit more bold. I'm having real trouble. I updated my program and was not prepared for it. But here we go. This cos squared plus sine squared is now a 1 because Pythagorean identity. minus sine theta, still all divided by sine theta, times 1 over 1 minus sine theta. And just like we saw earlier, I don't remember exactly where, but even though we don't draw them, there are implied parentheses around each of these pieces. Grouping exists within our fractions. Now, whether you actually draw these or not is entirely up to you. I don't really like to do so, but it might be helpful to help identify what we're going to divide out. But what I notice is I have a 1 minus sine theta that will ultimately be divided by a 1 minus sine theta. So they divide out, which means I'm left simply with 1 over the sine of theta. And by definition, and by gall, this is exactly cosecant of theta, sorry. And you know what? I'm feeling fancy. So we're going to go QED as the indication that we are done. Boom. These problems are tricky. There's no getting around it. However, if you persevere and you are comfortable in trying and possibly being wrong, I don't think there's any problems that we've seen or that we will see throughout any of this that you're going to be unable to do. So hopefully you found this video helpful. I did this prior to getting any emails, so if this was completely in vain, that's a bummer, but I don't mind it because you know I like the math. But I will see you in the next video where we will be looking at 5.3 and start solving some trigonometric equations. So, catch y'all later. Raiders.